Hello and welcome to this summary lectures on fundamentals of acoustics. We have come to the end of this series of lectures. So, I will just summarize what we saw. We started with the spring mass damper system, the transient plus steady state solution, and the idea was to understand mechanical impedance. Okay, Z mechanical, which is force over velocity at a single frequency. Okay. So, this is an idea seen from the forcing agent, how he perceives the system, and it is typically complex. It has a real part called resistance and an imaginary part called the reactance, and the reactance, when you set to 0, gives you a condition for resonances. Okay. This was a lumped system. Then we looked at two continuous wave bearing systems. One was a string, waves on a string, okay. These are transverse waves. Two, we saw longitudinal or quasi longitudinal waves on a rod. Both these systems have the same form of the wave equation, okay. And the solution, general solution, or let us say the harmonic solution, let me put a tilde, is of the form A e to the power of minus j k x plus B tilde e to the power j k x e to the power j omega t. Okay. I have remained with the e to the power plus j omega t convention throughout. Okay, that is to be noted. Now, this happens to be the right travelling wave, this happens to be the left travelling wave, and we interpreted this also as a tilde e to the power of minus j k x at a location x plus a tilde, a full travel and a reverse travel of L minus x and a modification of the boundary at the boundary. Okay. So this gives me a tilde e to the power minus j k x plus e to the power minus 2 j k l r tilde e to the power of j k x e to the power j omega t. Okay. One of the ideas put in was that every vibrating point on the string, every point has its own phasor. Okay. And it is referenced to some value which is e to the power j omega t. Okay. So that whatever this first point sees travels at a certain speed and with a phase lag of minus kx, it is seen at a distance x. Okay. So whatever is seen by the first point is seen by the point at x away from the first point with a lag of kx. Okay. This we saw using the crank and the phasor example. Okay. Out of this, one of the main points is k is the wave number, okay, and to be remembered as phase change per unit distance. This is the way you remember wave number, and therefore the phase lag over x distance is k times x. It is a non-dimensional number, it is a phase. Okay. Then we saw of course examples of finite systems and infinite systems. Infinite systems, forced, etc. with mechanical impedances at the end, and how to combine combined impedance at the driver, and then resonances, etc. Resonances, combined system resonances, combined system resonances. Okay. One of the reasons for seeing this is that if del 2y by del x square is 1 over c square del 2y by del t square, then for 1D acoustics the equation is del 2p tilde by del x square is equal to 1 over c square del 2p tilde del t square. Then we derived in detail the acoustic wave equation with the inviscid approximation. Viscosity is negligible in air, and linearity approximation, linearity. Okay. And we use the perturbation and we used continuity, which is one equation. You use momentum, which is 3 equations. Then we use the state equation, which is 1 equation, and we use the energy equation under isentropic, okay, isentropic conditions. Okay, so we have velocities, 3 velocities, which are 3. We have density, which is 1. We have pressure, which is 1, and we have temperature, which is 1. So we have 6 unknowns. And we have 6 equations. Okay, and we found the equation del square p dash or tilde is 1 over c square del 2p dash del t square. Okay, then we looked at the boundary conditions which are possible. Okay, pressure, homogeneous pressure can be 0, or del p dash del x can be 0, which is velocity, or an impedance condition where pressure over velocity is some condition. Okay. Then we saw 1D acoustics. 1D acoustics. Okay, a piston driven duct with either a closed rigid ended or open ended. Okay, that carries plane waves, and there is a piston which is moving it in a harmonic manner. Okay, and then the same solution holds a tilde e to the power of minus jkx plus b tilde e to the power of jkx e to the power j omega t, and of course the same interpretation minus jkx plus r tilde l kx e jk l e to the power plus jkx e to the power j omega t. This is the pressure reflection coefficient at x equal to L. Okay, and in this course our focus has been harmonic excitation, that is of the form e to the power j omega t, single frequency, that means single frequency excitation. And steady state response. Okay, so a PDE like this requires initial conditions requires boundary conditions, requires a force. Okay. Now initial conditions, the effect dies away due to dissipation, viscosity, or damping, let us call it a general term, damping. And this is reality. In reality this happens. So very quickly the transient dies away. So we are not interested in the transient. Okay. Although with Laplace transforms and Fourier transforms towards the end we saw special cases. Okay, we saw special cases so that we know how to deal with it, but that is not the norm. Okay, we did this so that we have the knowledge how to do it. Then with respect to boundary conditions, you can have homogeneous boundary conditions, that means zero value boundary conditions, and then you apply a force. Okay, so this is one combination. Or you could have a forcing coming from the boundary, like an oscillating piston. Okay, the boundary condition itself provides the excitation, not necessarily force as in force units, but the boundary excites the system. Okay, that is the other form. Okay, so we have seen both of these. Okay, so then we did a few more calculations on 1D using source strength and pressure reflection coefficient at x equal to L and so forth. And we also saw power calculations. Okay, power is 1/2 the real part of F into velocity conjugate. Okay, something to remember. And in here we introduce the idea of specific acoustic impedance. Which is pressure over particle velocity, which is at a point, it is a point property. Okay. Then I continued with this and addressed this as acoustic impedance because it is a very long word. Okay. But pressure over particle velocity is specific acoustic impedance. Okay. Then we moved to the free space Green function, which is a solution to del square plus k square g of r comma r dash is equal to minus delta of r minus r dash. Okay. This is the receiver point, this is the source point. So this is the solution. Okay, and the form is fixed for this free space Green function, which is e to the power of minus j k r by 4 pi minus r dash. Okay. Then from here we went and derived the Kirchhoff-Helmholtz integral equation, okay, which puts the acoustic wave equation, partial differential equation, in an integral form. Okay. So what we get is phi at a receiver location r dash is an integral over a surface where you have G del phi dotted with N minus phi del G dotted with N over a surface area. Okay. So, this form is the same for interior or exterior acoustics. And N points in the direction away from the region of interest. Okay. This G is composed of R and R dash. So, ds works on R. Okay. Now, so the form of Kirchhoff-Helmholtz integral equation is the same for interior and exterior acoustics. Okay. Then we went into exterior acoustics. And we saw a pulsating sphere. So, there is a sphere that its radius oscillates harmonically. Okay. So, A plus delta of t or A plus delta e to the power j omega t, that is how the radius goes, okay, uniformly in and out. If we said this is a model of a speaker, okay, then we saw this using the KH integral. Okay, let me say before that we derived the Dirichlet and Neumann-Green functions. For the spherical coordinates. Okay. And let me see. And before that, we took a look at the acoustic wave equation in spherical coordinates. Okay, using separation of variables. So, we got into spherical Bessel functions, we got into Legendre and associated Legendre polynomials, we got into, of course, the e to the power im phi term, which combined gave us the spherical harmonic. Okay, we saw their behavior using curves, we saw the orthogonality relations, we saw the recursive relations, and so on. Okay, using graphs, we plotted graphs to see how they behave. Then we derived the Dirichlet-Neumann-Green functions for the interior and exterior acoustics. Following this, we started looking at exterior acoustics first, and we looked at the pulsating sphere. Using the Neumann-Green function okay, exterior Neumann green function, okay. And then we looked at pulsating sphere using boundary matching technique. And we also use the separable functions and showed how the green function, the Neumann green function could be derived, or same form could be arrived at. Then we saw the physics of the pulsating sphere, okay, for values Ka much less than 1 in the monopole range, how it is a poor radiator, then Ka when it goes much, it becomes an efficient radiator. How in this case the surface specific acoustic impedance is largely imaginary, and how in this case the impedance is largely real, okay. And then also we saw how in the far field, or let us begin with the near field, how in the near field of the pulsating sphere or of a source, the particle velocity has an in phase component and an out of phase component, okay, which is in case of the sphere had a 1 over square dependence and this had a 1 over r dependence, whereas the pressure had a 1 over r dependence, okay, j over r and j over r I think. So that in the far field, the particle velocity is in phase with pressure, okay. And so you have plane wave impedance, plane wave acoustic impedance and power transfer, and so easy power measurement, easy and accurate power measurement. Okay, at a distance from the source, in the far field of the source. Whereas in the near field, which is dominated by the out of phase component, okay, it does not mean the in phase component is not there, but is dominated by the out of phase component of velocity, and in computing or measuring power, averaging is done, and when you average 1 over r which is out of phase and 1 over r, 1 over r which is in phase and 1 over r square which is out of phase, and in the near field this dominates, then averaging can be inaccurate, so that the result will be erroneous. So you have to be in the far field so that this component has died out. Then this component is in phase with pressure and you can get accurate measurements. This is regardless of whether the source is efficient or not efficient. Source could be in this range, or source could be in this range, or source could be in this range, etc. But you had to be in the far field to do your measurements. I will close the lecture here. I will summarize my comments in the coming lecture, next lecture. Thank you.